Of notes, we're going to be continuing our expanding our toolbox for detecting whether or not a series converges. And so last time we talked about the divergence test, which can be used to determine, or at least to identify some series that diverge, and the integral test, which can be used to determine the convergence of a series if you can integrate an associated function. So today we'll be talking about 4 different tests: the direct comparison test, the limit comparison test, and the ratio test. So I guess that's 3 different tests here, and we'll start with the direct comparison test. So this is not one that's discussed directly in your book, but it is included as an exercise. So if you'd like to see the exercise that the book uses to introduce this, you can look at exercise 8 from after the section 8.3. All right, so I want to start with a couple of examples of these 2 series that you see here. And as you look at these, right, our main goal is to think about, and for these kinds of tests, whether or not a particular series converges. And so if you look at these, at least to me, it's not obvious how to determine the convergence of these series, or it wouldn't be easy to do using techniques that we have already. So we want to think about some alternate routes we have here. And as you look at it, you might start to kind of guess, at least for this first series here, it's a reasonable guess that the terms that you're seeing as the index gets larger, so the end behavior, again, that's what matters for convergence, these numbers, 1 over k cubed plus k, are getting really small pretty quickly. And so we might be tempted to think that this series converges. So I've gone ahead and actually sketched in the 2 series here so that we could look at those. Now, with the comparison test that we're thinking about now, what we're interested in is trying to find out if there's a similar series that we do know the convergence or divergence of that can help us determine our series. And it turns out that this is very similar to the comparison test for improper integrals. So in our first example here, with the series 1 over k cubed plus k, okay, I have it plotted here. So for k equals 1, 1 over 1 cubed plus k is just 1/2. Then we increment to 2. So we have 1/2 plus 1/9 plus 1/30, and so on. And so we're noticing that these terms are going to 0 very quickly. And in fact, if we think about what's happening, for large k, the denominator of the fraction here looks a lot, the main term here is the k cubed. So we might consider the related series. So I'll just write this down here. 1 over k cubed. So we've seen, in fact, that that this series converges. And so because the terms of our original series look kind of like this, we might that's some evidence that our series also converges. So let's go ahead and plot the terms of this series, right? So we know this one converges. Let's just write out the first few terms. 1 over k cubed when k equals 1 is just going to be 1 plus, 1/8 plus 1/27 plus, and so on. And so if I plot this, I have the purple dots here. And what you notice here is that that in this case, the purple series is always greater than the blue series. So for all k, 1 over k cubed is greater, okay, so for all natural numbers k, 1 over k cubed is always greater than or equal to 1 over k cubed plus k. And so therefore, when we sum them all up, this sum is going to always be greater than the sum from k equals 1 to infinity of 1 over k cubed plus k, right? We're interested in this sum here, but what we know is that the sum on the left is finite, right? So this sum converges. Hence, we can conclude that the sum, I'm going to go ahead and when I give you these notes, I'm going to go ahead and add some extra space here so that we can have room for your notes on the second part here. So what we conclude then is that the sum, let me go ahead and space this out a little more, conclude then that the sum we're interested in, k equals 1 to infinity, 1 over k cubed plus k, converges. Okay, so let me just kind of review that logic then. So I'll go ahead and just write it up here. The sum of the purple terms converges, and each blue term is less than the corresponding purple the blue series must, and maybe I'll write it in a parallel fashion, the sum of the blue terms must also converge. Okay, now, notice here that this is meant to be corresponding. I'm just noticing here corresponding purple terms. Notice here that this works because our series here, both the purple and the blue, are always positive. Right, and so we do need these terms to all be positive in order to conclude that because the purple always lie above the blue, then the blue must also converge. Okay, so this should feel very similar to the comparison test for improper integrals. I want to now go to the other type of comparison that we might make, right? And so that is, let's go ahead and add an extra page here. So I'm going to go ahead and click here and add a page. And I'll add a corresponding page to your notes as well. So now here, if we look at the sequence 1 over ln of k, and we're thinking about summing those terms, right? We're starting our sum at k equals 2 because we have we want to avoid a 0 in the denominator here. Starting at k equals 1, the first term would be undefined. So we're starting at k equals 2 here, and I've plotted some of these, not really to scale, except noting that 1 over ln of 2 is bigger than 1. And here, okay, so you can see that ln of k is actually, it does grow towards infinity, so the terms are going towards 0. So that means we cannot use the divergence test. So this series might converge or it might diverge. Terms are going towards 0, but they're going towards 0 pretty slowly. And in fact, they're going towards 0 more slowly than just 1 over k. And we know that the harmonic series, the sum of 1 over k, actually diverges. So that was a main theme from the last set of lectures. So let's consider that as our comparison. So let me go ahead and consider the sum from k equals 2 to infinity of 1 over k. So that's going to be 1/2 plus 1/3 plus 1/4 plus ... Now, we analyzed the harmonic series, which starts at k equals 1, typically. But because convergence doesn't depend on the first term, if you add up all the numbers, including 1 here, then you would have an infinite sum. Well, if you take out that first term, you still have an infinite sum or a divergent series here. So this series diverges. But notice here that 1 over k is strictly less than 1 over ln k for all k bigger than or equal to 2. Right, and so here, what we then would conclude is that the sum of 1 over ln k is greater than or equal to the sum from k equals 2 to infinity of 1 over k, which is, I'm going to go ahead and just write which equals infinity, right? That's a type of divergence. So series diverges. And so because our series at every point is greater than a divergent series, so I'm going to go ahead and just, let's go ahead and get rid of that. We're going to add in the harmonic series terms here. This is going to be 1/2, 1/3, 1/4, 1/5, and so on. Because our series in blue is bigger than a divergent series for every term, then we would conclude that our series also diverges. So this will be our summary here. So because each purple term is less than each blue term, and the sum of the purple terms is infinite, then the sum of the blue terms is also infinite. Okay, so that's essentially the comparison test, the direct comparison test in a nutshell, and you can see the similarities with the comparison test for improper integrals. So let me go ahead and just give you the formal definition here. And so here we need to suppose that for every k, we have, and what I've done here is just write this compactly the way your book has it. So we have one series bk that's always less than the series a. So each term bk is less than ak, and we always have positive terms here for both series. And that's very important. Okay, so the idea is then that if the sum of the AKs converges, then so does the corresponding sum of the BKs. Now, in your book, they don't actually include indices. It's not necessary to include indices just because, again, convergence depends on the end behavior of your series. So what happens in the first few terms doesn't really matter. But I'm going to go ahead and just put this in here anyways. And again, what we're saying here now is that if we have that if we have a convergent series that's bigger than our unknown series at every term, then the unknown series must also converge because its sum is less than the finite sum of than the sum of the BKs, which is finite. And on the other hand, if the sum of the, this should be diverges. If the sum of the BKs diverges, then so does the sum of the AKs. And so here, I just want to highlight a couple of things that you need in order to use this test. So in order to use this test, you need to first you need to have a conjecture or a guess about the convergence of your series. Okay, and then you need to find a comparison series. Okay, and the comparison series needs to be a convergent series whose terms are bigger than your series. If you guess that your series converges, and on the other hand, if you have guessed that your series diverges and you want to show divergence, you need to find a divergent series. Whose terms are smaller than your series. And all of the series must have only positive terms. So this is to show divergence. So in particular, you'll need to kind of have in mind some convenient comparison tests that you can use. And you'll see by doing some examples that there are some kind of usual suspect types of series that we've computed and talked about that will be useful. So, okay, I'm going to go ahead and give you some time to try some of these problems here. So go ahead and use direct comparison to analyze these two series. So notice here that that we'll need to, so you'll need to perhaps be a little bit clever here about how you create your comparison function. So in this particular case, I guess I'll say that I think the second one here is perhaps a little harder. So first come up with your conjectures and then try to find a comparison function that has the right properties.